Okay, so I hope this works, right? Yeah, okay, so apparently my stream just stopped for some reason, and yeah, I guess I'm back now, but yeah, it's super weird. Yeah, I'm just gonna go and fix one thing. All right, I guess I'm back again. For some reason, the stream just stopped. I don't know. But anyways, let's carry on. So by varying the weights and the thresholds, we get different models of decision making. For example, suppose we instead choose a threshold of 3, and the perceptron will decide you should go to the festival whenever the weather was good, or when the both of the festival were near public transit or whatever. And your boyfriend or girlfriend was willing to join. In other words, it would be different model. Right, so obviously the perceptron isn't the complete model of the human decision making, but we can illustrate is how a perceptron can weigh up different kinds of evidence in order to make decisions, and it should seem plausible that a complex network of perceptrons could make quite subtle decision. Interesting. Yeah. So let's just paint this, I guess. So there are 5 inputs to each and every perceptron, right? And every input should have an input in the perceptron as well. Then we have 4 other so yeah. I'm gonna try to find out a way for us to actually visualize this networks, but that will be another time. I just have to understand first the actual mathematics behind everything, and then we can visualize it by using the mathematics itself, I think. And it's good to have like these kind of visuals to actually understand what is happening. But yeah, we're gonna try to visualize neural networks. That's gonna be fun. And then probably like try to integrate it with PyTorch or whatever. Let's see if that works. And then we have the output. And I also think the reason why my that stream stopped is because I had a VPN going on my computer, so it changes like location. So in this network, and I think so this is the first layer, first, second, first layer of perceptrons is called first layer. Making it three very simple decisions by weighing the input evidence. What about the perceptions in the second layer? Each of those perceptions is making a decision by weighing the result of the layer. Yeah, so it's like weighing the result or the chain reaction, I guess. And okay, that makes sense. The layers are weighing each other. So the layers are weighing each other, and by this formula up here. That's actually really good. So the perceptions themselves actually have the same output, but the arrows in this picture here, these are the same values. It's the same output, right? But it's to the different perceptrons. So it's just how it's connected, but the output is the same. Let's simplify the way we describe perceptrons. The condition is cumbersome, and we can make two notational changes if we simplify it. The first change is to write as a dot product, where W and X are vectors whose components are weights and inputs, respectively. The second change is to move the threshold to the other side of the inequality and replace it by what's known as the perceptron's bias, which is actually equal to the negative threshold. Using the bias instead of threshold, the perceptron rule can be written as this here. So the output, let's see, output is equal to 0 or 1 if W with a dot product of X plus the bias, right? So it's the inputs with the dot product or the matrix multiplication with the W, which is the weight, and then we just add the bias, and then we check if that is equal or smaller or equal to 0, and then we do it as with the same function. but checks if it's greater than 0, and then it becomes 1, right? That's really good to know. Since these are vectors, I guess 0 means that we have a 0 matrix, so all the values in the matrix is going to be 0. That would make sense. I'm just gonna go and check one thing here. Right, okay. So that's good to know. You can think of the bias as a measure. Oh yeah, bias is equal. That's good to know. Bias is equal to minus threshold, right? You can think the bias of the measure of how easy it's going to get to the perceptron to output of a 1. Or to put it in more biological terms, the bias is measure of how easy to get the perceptron of fire to the fire. Obviously, introducing the bias is only a small change in how we describe perceptrons, but we will see later that it leads to further notational simplifications. Because of this, in the remainder of the book, we won't use the threshold. We will always use the bias, but so threshold is bias is equal to minus threshold. I've described. Wait, can you guys hear me? Yeah, I think. Okay, so you guys can hear me good. So here we have. I've described perceptrons as a method of weighing evidence to make decisions. Another way perceptrons can be used is to compute elementary logical functions we usually think of as underlying computations. Functions as bitwise and, bitwise or bitwise NAND. For example, suppose we have a perceptron with 2 inputs, each with weight -2 and overall bias is 3. Here's a perceptron. Okay. So just to like give a very easy understanding of what the perceptron actually is and how it works, so we can just write them. So I guess the x1 and 2 is the inputs, the -2 is the weight, and 3 is the threshold, I think. Then we so each weight with -2. Yeah, okay, it basically says that. So let's write that on. It's equal to weight, and 3 is equal to bias, I think. Yeah. So we have -2 as a vector. He's not writing vectors as I like to do it. I like to use square brackets because that represents an array in Python. But makes sense still. So the input here is 0, I think. Yeah, that makes sense. And then we... Is it plus the bias? Wait. It's plus the bias. I think that is... Okay, so the bias is 3, but the threshold is -3. Makes sense. which is greater than 0, which means that output is equal to 1. Nice. We have introduced the star symbol to make the multiplications explicit. Similar calculations show the inputs 0, 1, and 1 and 0 produced output 1, but the input 11 produced the output red -3, which is negative. So our perceptron implements an NAND gate. Very interesting. Very interesting. You could technically, like, you could wait, so wait a minute. NAND gates are used to create hardware, or it can be used to create VGPAs, which is like a programmable hardware. And this could technically like simulate that hardware. That's interesting. The NAND example shows that they can use perceptrons to compute simple logical functions. In fact, we can use networks of perceptrons to compute any logical function at all. The reason is that NAND gate is a universal for computation. That is, we can build any computation about the NAND gates. For example, we can use the NAND gates to build a circuit which adds 2 bits, 1 and 2, or x1 and x2. This requires computing the bitwise sum, right? And as well as the carry bit, which is set to 1 when both x and 1 are 1, the carry bit is just bitwise. Yeah, okay, so this is actually really great. I want to write this off. This is great. They are basically combining basic material from university with this type of comparison. It's great. So this is equivalent of the network perceptrons. We replace all the NAND gates by perceptrons with 2 inputs, each weight of -2, and overall bias is equal to 3. Here's the resulting network. Note that I moved the perceptrons corresponding to the bottom right NAND gate a little, just to make it easier to draw the arrows on the diagram. All right. So here's like a very similar network But we have to make sure that we know that the W is equal to -2, the bias is equal to 3. Yeah, that's it, I think. Ah, I failed. I failed right in this. No. One of the notable aspects of this network of the perceptron is that the output from the leftmost perceptron is used twice as the input. Yeah, that's what I thought about, so we can just write like... Technically, this whole thing could be the output. This whole thing could be like an output of the carry. We don't even need this, I think. Yeah, we actually need that. Never mind, we need that. We need that. Never mind. Yeah. Yeah, so you can just merge. If you don't find this obvious, you should stop and prove yourself that this is equivalent. With that change, the network looks as follows. Yeah, that makes sense. Up to now, I've been running inputs like x1 and x2 as variables floating to the left of the network perceptrons. In effect, it's conventional to draw an extra layer of perceptrons, the input layer, to the end code of the inputs. Right, so we should technically write it like this. Yeah, makes sense. This notation for input perception which it doesn't actually mean the perceptron we it's to see this, we suppose we have a perceptron with no bits. Yeah, I guess, guys, that's have to be everything for today. I am a bit tired and I have to wake up quite early tomorrow. So, thank you guys for watching and have a great day. Oops.